Good morning, everybody. It's my pleasure to introduce Jório. I would like to speak some words in Portuguese to introduce him. Ado é pesquisador, né, especialista em Near Field Raman, e ele, além de trabalhar com pesquisa em Near Field, ele também está trabalhando com instrumentação. Tem vários trabalhos importantes na área, né? Em diversos temas bem diferentes. Então, tem trabalho com proteína do Alzheimer, trabalho de picos Stokes e anti-Stokes da luz, né? Então, são coisas bem diferentes, desde ótica fundamental, né? Ótica quântica fundamental, até aplicações em biomedicina. E é um prazer, né, te receber aqui, Ado, te agradeço por aceitar o convite. E, do ponto de vista pessoal, o que eu posso falar é que, além de ser um pesquisador brilhante, o Ado é um colega muito solícito, muito bacana, uma pessoa muito generosa, né? Então, para nós é um prazer tê-lo no departamento e um prazer receber aqui. Então, Ado.
So first, I would like to thank the organizers for the opportunity to be here and share with you this talk. So I was told I'm allowed to remove my mask, okay? No one in the audience is allowed, but I am, because I'm very far away from you. And I think it will improve the quality of our communication. So before entering the topic of Phonon and Electron localization two-dimensional systems, let me start a little bit more broad, okay? There is one interesting study aspect in economics that are related to the technological cycles, okay? If you go back, this was introduced by Kondratiev, a Russian economist. And if you go back, you see the Industrial Revolution in 1771, the age of steam and railways, the age of steel and heavy engineering, the age of oil, and then here I point your attention to electricity, automobile mass production, the age of information telecommunications. And what they show is that the organization of our society and even the economy, the world economy, changes very much every time you have one of those technological innovations. And we are clearly in a, let's say, in a depression of the economic situation, of the economic structure of capitalism. And we point, it's very clear that this points to some sustainable economy, some sustainable society. And this has to do not only with everything we like plastics that we produce and consume a lot, but also with energy. We have the search for green energy, for green hydrogen, and all these things have been guiding the science that we do. We do, of course, to understand, we look for science to understand nature, but we also have these worries to structure our society. When you go to material science, one candidate, one aspect that has been largely studied, I can say it's the wave of material science today, is these two-dimensional systems. You have atomic thin or a few atom thin structures. And when you look at the electronic structure of these systems from, let's say, hexagonal boron nitride that are insulators, and you have transition metal dechalcogenides or phosphorine that are semiconductors with different gaps. And you have graphene that actually triggered all these studies. And graphene is a semi-metal or a zero gap semiconductor, as you prefer. And when you go to different applications, for example, if you go to photonics, to every use of photons on telecommunications and everything, you see that you can spend most of, well, a large area of the electromagnetic spectrum with these materials. And if we focus here on graphene to speak about the richness of these systems, if you start to stack them, because you have the system themselves, they have their properties, but if you stack them, if you put one on top of the other, you have an extra richness. So this is a sheet of graphene, okay? So this is single layer graphene, but if you put another layer on top, you now have a different system that is a bilayer graphene. They are different from the electronics point of view, etc. And notice that the stable structure of bilayer graphene, which is also the stable structure of graphite, is having one atom of the top layer at the center of the hexagon of the bottom layer. But then people realize that if you start to rotate, you have the formation of the so-called Moiré patterns that are those superstructures that appear when you have two periodic lattices that are rotated one with respect to the other. And this generates a new concept it's called Twistronics. So the Twistronics would be you controlling the electronic properties of the new material by changing the twist angle. So let's see what is the Twistronics of graphene, okay? Although I'm using here graphene a lot as a prototype material, but this has been studied for all the two-dimensional systems, okay? So basically, when you have one layer rotated with respect to the other, as shown here by angle theta, you will have, as I already showed, you have a superstructure that is given here by these two lattice parameters here, these two lattice vectors. And consequently, if you take the Fourier transform of the real space and you go to the reciprocal space, the space of the waves, you also change the reciprocal space of the two lattices by an hexagonal reciprocal space given by these two arrows here. So you enlarge the size of this unit cell in the real space and you reduce the size of the unit cell in the reciprocal space. And this will generate some interesting physics, some interesting phenomena. Like, for example, this is the Raman spectrum. This is Raman shift or Raman frequency as a function of intensity. And every spectrum that you see here is for one given material with one different rotation angle or twist theta. This peak here, I will talk a little bit more, is the usual peak of graphene, but then you see the appearance of many peaks that are pointed by stars here, okay? These large guys here come from the silicon substrate. Every time you have a material, a two-dimensional material, usually it's sitting on a substrate and you also have the substrate. But let's give a step back. What I was showing you was the Raman spectrum of graphene, of twisted bilayer graphene. So what is the Raman spectrum? If you shine light on the material, the light, the photon, may lose energy to a quantum of vibration in the system, to a phonon, and the scattered light will be shifted from the incoming light from the laser by the phonon energy. So by studying the scattered light, the inelastic scattered light, you have a lot of information from the material. And if we look into graphite or graphene, what we have is one very strong peak at a Raman shift, which is usually measured in wave numbers, okay? There's an upward energy for some. And what you are seeing here is basically this displacement of the scattered photon with respect to the incoming photon due to the generation of one quantum of atomic vibration that is represented by these movements here. So this would be the graphene at the equilibrium situation, but then you have the stretching of the carbon-carbon bands. This stretching has a given frequency. This frequency is dictated by the mass of the carbon and by the strength of the bonding, of the chemical bondings. So this vibration here brings you information about, indirectly about the thermal properties, about the mechanical properties, the electronic properties, etc. Okay, so if I go back to the picture that I was showing you, so this vibration is actually imaged here at, as I said, at near 1600 wave numbers. And when you look into the phonon dispersion relation for graphene, this is equivalent to this point here. So this is what you see, okay? But when you have twisted bilayer graphene, as I told you, you reduce the reciprocal space, the Brillouin zone. And what you are doing is you are activating phonons in the interior of the Brillouin zone. And actually what you see with all these peaks here, you can map the entire phonon dispersion relation of graphene just by rotating these two layers, okay? And this is something very unusual, special, because if you want to map all the phonon states of any material, usually you need neutron scattering or X-ray scattering, because you need very small wavelength so that you can probe these large Q vectors. But here you can do it with the struct, let's say, of twisted bilayer graphene. And if you go to the electrons, you also have a very interesting and rich phenomenon, okay? If you look into any electronic dispersion relation, and every time you have a dispersion relation that has a zero derivative like this, usually you have a high density of electrons at that specific angle. And what you have when you do this twist game, let's say with graphene, is that you can change the spacing between these two levels. Usually the Fermi level is up here. So below this level in energy, you are full of electrons, and above you have empty spaces. So you can excite one electron from here to here with light or other excitation. And what we notice is that, again, the angle controls this gap. And if you do, for example, if you do an optical absorption on graphene, you have a peak in the absorption and in the reflection, and the energy of this peak will change when you rotate the angle. And it changes quite substantially. It changes from zero, that is the zero gaps semiconductor, up to almost 3 or 4 EV, okay? And if you go now, here I was showing you a rotation angle of 21.8, 13, 9. And now if you go to very small angles, like what the so-called, now called magic angle, the magic angle is around 1 degree of rotation. You have also these high density of states happening at a small energy. Notice here the energy here is very minor. Here was in the order of 1 electron volt. Here is on the order of 0.1 electron volt. But something special happens at this very specific angle, which is the formation of flat bands near the zero energy level. And these flat bands, when you now plot the density of states, you will have a high peak of density of electrons at this zero energy, which is where transport really usually happens, where excited electrons will transport current and all these things. So at this very specific magic angle is where graphene becomes superconductor and exhibits other very interesting correlation phenomena, correlation of electrons, phonons, and electron phonons. Okay, and it's not everything. If you go below 1 degree, you also have something very interesting happening. Here you have these 2 layers of the bilayer graphene represented by the gray and red dots. Okay, each dot here is 1 carbon atom. And if you notice at those regions here is where 1 atom of the top layer, let's say the gray, falls exactly on top of the atom from the bottom, that is the red. So this would be called the AA stacking. You have one exactly on top of the other. And at these very corners here is where it happens, what I told you before, is the stable situation. The atom of the top layer falls exactly in the middle of the hexagon formed by the bottom layer. This is the so-called AB stacking, and this is what is more stable for graphene, for bilayer graphene and for graphite. But what happens when the angle is too small? When the angle is too small, the system is unstable, and the room temperature thermal energy is enough to make the system rotate back and restackle in the more stable AB structure. So what you will have is triangular shaped areas of AB stacking, but because the region that was here rotates to get to the stable situation, it rotates to one direction, while in the nearby, it rotates to the other direction. This happens with the formation of a domain wall. This is a place where you have a strong strain and the stacking is not there, okay? So this is the reconstructed twisted bilayer graphene on very low angles. Okay, so here is a summary. Graphene is hexagonal, so every 30 degrees you have a repetition of the structure. So if I plot here from 0 to 30, what happens from, let's say, the large angle rotation is that you can, for example, control with the rotation, you can control the energy of absorption and reflection of graphene. If you go to this very specific magic angle, you have correlation phenomena, you have superconductivity observed in graphene. And if you go below that, you have the atomic reconstruction and you have the formation of the domain walls. They are called strain solitons. And you have the AA sites that are called sometimes topological defects. Okay, so I spoke a lot about graphene now, so now I move to nano optics, and later I will join the two, okay? So what is the problem? What is the challenge with nano optics? Everybody knows that if I have a wave going through an aperture, if this aperture is much larger than the wavelength of light, the light passes through mostly, let's say, linear, and then you can use the usual optics, the linear optics that we do with, let's say, when every time when the dimensions are much larger than the wavelength of light. But if I reduce the size of this aperture here, you have diffraction of light, okay? And what happens with diffraction of light is if you have two objects that are emitting light, and when I say light here, I'm talking about the visible range, okay? Of course, if you go to X-ray, gamma ray, that would be different. But let's be on the optics, okay? On the usual regime that are wavelength in the range of 400 to 700 nanometers. So if the distance between these two objects is much smaller than the wavelength of light, the real number is given by this, okay? This would be the wavelength of light, and this angle here is the numerical aperture. So there are some place, but in general, if this distance is in the order of the wavelength of the light, you cannot distinguish the two objects. Okay, and this is the problem of introducing nano optics. This limitation of optics is known for a long time. Okay, so we have here this limitation was introduced by Abe in 1873. But then I go very quickly on the history of nano optics here, saying that in 1928, a researcher called Ernest Singe, he exchanged some letters with Einstein at that time, saying that there would be, you can do nano optics. You just need to go very close to the object emitting light, so close that you are far away from the other object. So you would not be in the regime that we call far field, that is where the light is propagating, but you would be on the regime of the so-called near field, that is very close to the object. You obtain the information only from that object. And to do this thing technologically, we had to wait for a long time. And the nano infrared or nano photoluminescence happened in the 1985, but the nano Raman happened. One possible, let's say, candidate for the first one who did it was Renato Zanobi at ETH. And then you see that these dates of the year 2000. And what they realized was, okay, they illuminated the sample here, and this illumination is restricted by the diffraction limit of light. So with a microscope, you can only focus light within half of the wavelength of light. But then if you come with a nano antenna and you capture the light very close to the object, then you can enhance very strongly and see, for example, the Raman emission from one single molecule. And this is the so-called tip-enhanced Raman spectroscopy. Okay, this is the Raman spectrum of this molecule, and they enhanced locally with this nano antenna. And why did it take so long? Because to implement this, we had to wait for the development of scanning probe microscopy. So when we had AFM and STM showing up, we could just metallize the tip, and the tip metallized generates the antenna that you need to do this near field optics. And of course, to implement this, let's say that this is a simple spectrometer. Okay, so you have laser shining light. So the laser shine the light on the object, and then you can focus it with a microscope, with an objective. And this goes back to the detector, and then you analyze the scattered light. And the phonon that is created remains on the material that is somewhere here. Okay. To implement nano optics, you need a little bit more sophisticated equipment. First, because you have to play with the optics to generate an optical mode that is able to couple to the nano antenna. So here is a zoom to the nano antenna that's placed here, okay? And there are different ways for you to implement this, but the one we have in the laboratory, this is a scanning probe system controlled by a tuning fork. So the tuning fork has a specific frequency of vibration. And when the antenna approaches the surface and starts to sense the surface with, due to the van der Waals forces, you change the vibration of the tuning fork. And by changing the vibration of the tuning fork, you, with all the electronics, you sense the approximation and where are the objects that you want to image. And here are two examples. What you see on your screen now are graphene layers that were bombarded with a helium gun. Okay, so with a helium gun, we made the drawing here. Okay, the helium is a very sharp beam that can make drawings with a resolution of, let's say, 10 nanometers. Okay. Here is the scale. This is half of the wave, half of a micron. So this is the limitation of usual optics. And you have these two drawings here. And what we are imaging is the Raman signal coming from defective graphene. So the graphene is full of defects here, and it's not defected here, okay? And when we land the nano antenna and scan, we see that now with more resolution, that what was drawn here was the world map. And here is the logo of my institution, of UFMG. So this is what we can do. And just for your curiosity, this is a photo of the equipment with two ex-PhD students. Okay, they were not physicists, they were electroengineering to develop all these machinery. And here I always thank very strongly Lucas Novotny, that he is a researcher today at ETH in Zurich. And he gave me all the basis to start this work some 15 years ago at UFMG. And from there, we moved. Okay, but the most deep physics on this nano optics is related to the nano antenna. So you have to design a antenna that is very efficient to do the optics that you need. And this is the shape of the antenna that we have. This is a cartoon of a twisted bilayer graphene. And here would be the laser illuminating what we can call here a very large area. Okay, so when we are in the world of nano optics, the focus of a microscope is within like 500 nanometers, and we want to watch at 1 or 10 nanometers. Okay. And when I told you that the design is very specific, is the following: you have this nano pyramid that is sitting on top of a micro pyramid. And at the very end, the structure you have is like this, okay? So you have a plateau here that's like a mirror, and you have this nano pyramid with a size L. And of course, you have waves of plasmons here. And like the strings of a guitar or anything, you have the resonance modes. And there will be a very specific L for a very specific laser that will be in resonance. Okay, so this is a calculation made for a Rini laser, that is the red, the usual laser that you have in laser pointers, showing that when you change the size of L, you have resonances, and these resonances are related to matching half of wavelength in this plasmonic wave. And we have a maximum here that happens when you have exactly L equals 400 nanometers. And this plateau here is very important because you are entering resonance, not with this pyramid as a resonator, but because of this plateau, you can think of imaging charge in electromagnetism. And this acts actually as if it was, let's say, a pyramid shape like this, but with a sink of electrons that is very effective. And this is why you have a very high peak here. And if we had just a pyramid like this without this structure, the resonances we would have would be those. And this gain here in efficiency, and what we are imaging here is the intensity of the field at the very edge of the structure. This gain in efficiency makes this tip very, very good, okay? So, and one other technical aspect is how to build such an antenna, and you build it using very well-established silicon technology, okay? So designing things in silicon is what the previous industrial revolution gave us, all this, the semiconductors, all the computers and everything. So you have a silicon wafer, and the silicon wafer has a silicon oxide cover, and then you open a hole and you throw an acid, and the acid will corrode only the silicon, not this silicon oxide. And the corrosion will happen following the crystalline structure of the silicon. So this happens, nature gives you that. And by controlling the time, you stop the corrosion at the very specific time you want, and then you cover again, and then you open a little hole, and you finish the job. Okay, so here you made the shape in silicon that you need for your nano antenna, and then you evaporate gold, and you come with a glue, a resina, and you remove the gold. So this is the antenna that you now will shine light from here. Okay, and again, what this antenna do is, what it does is, okay, when you approach the antenna to the surface, you will have, before you had an illumination area that is represented by this green, green circle here, and then you measure a Raman spectrum that is here, okay? And then when you land the antenna, when you approach the antenna, you will enhance the field very strongly only at the apex of the antenna. So in a very small place here that is in the order of 10 nanometers. And even so, the signal, because the antenna is very efficient, the signal gets highly enhanced. So the signal coming from all the illuminated area become negligible with respect to the signal that you are measuring locally at this very specific point. And here I point your again attention to the fact that what we are imaging here is the vibration of the carbon-carbon stretching that I already told you. And you all also have some second order modes in graphene that I will not go too much in detail, like you can also probe the breathing of the hexagons. And this specific mode here has some interesting aspect that I will talk a little bit later. Okay, so what is the achievement that you get with the nano optics? This is one very famous paper in this area, where this is a piece of graphene, and what the authors, these Korean people, what they did, they colorized the graphene. Every pixel here is one Raman spectrum that was took from a specific location in this graphene, and the color here renders the frequency of the Raman peak. And the frequency of the Raman peak, the authors showed this, they are related to either strain or doping in the material. And with strain and doping, you change many properties of the material, okay? And they show that when you have graphene sitting on a substrate, the graphene is naturally showing inhomogeneity on the strain and doping all over. Okay, but this was made with a microscope. So every pixel here, the distance between one pixel and the other is 1 micron. And if you go at this very 1 pixel here and you look with the nano optics, you see that at this very 1 micron location, you also have inhomogeneity, but now you are looking at the nanometric level, okay? Okay, this is just to show the difference between the micro and the nano, but let's see, for example, electronics is strongly based on PN junctions. If you have a P-doped material and an N-doped material and you place them together, at the interface, there will be migration and you have the formation of what we call depletion layer. Controlling this depletion layer make you possible to control yes and no current and like diodes and transistors and things like this. Okay, but this is very small. How to image this? You have, of course, to produce one. Let me, this is not really a PN junction. This would be a PP prime, okay? If you take graphene and you place graphene on a substrate like glass, it will get P-doped. But if you put talc, that is another two-dimensional material, on one piece of graphene, the talc dopes P much more strong than the glass, okay? So this is doped and this is doped, but this is much more highly P-doped than this region here, okay? And if you do the if you measure the spectrum here and you measure the spectrum there, you see the blue and the red here that the peaks change. They change in frequency, they change in intensity. And it is understanding these changes that was made initially by these Korean groups that gives you information about doping. And if we now go with the nano optics, the image you have here, this is on top of a graphene. But here you are, the graphene is on top of talc, and here the graphene is on top of SiO2 or glass, okay? This is on a glass cover slip. And this image that you have here is the topography, is the AFM, because the nano antenna, at the same time that is doing the nano optics, it is also doing atomic force microscopy. So you measure here the difference in height, so you know that the junction is here. And now if I measure the intensity of a given peak, I see that there is intensity oscillation when I cross the junction. And if I make a plot here of the intensity ratio between these two specific peaks here, I'm not going too much into details, you see that this intensity ratio goes up, down, up, and then is stable. And what you are doing here is directly imaging the depletion region of this P prime homojunction. All right, but now let's go back to the twisted. I was talking a lot and saying that the twistronics is very interesting. So let's talk about the twisted bilayer graphene, and reminding you that if I have the very low angle, I will have these reconstructed areas with the domain walls. Okay, so these two images that you have here, this image comes from Nano Optics, and this image was obtained again at the same time is the atomic force microscope, is the topography. So notice that you have some dust, some things here that you also see in the spectroscopy. Like here, you have this thing here and this thing there. But notice that the places where graphene is very clean, you see nothing on topography, but in the spectroscopic response, you clearly see those triangular shapes related to the reconstructions, okay? Just, Simone, I should go up to what time? Sorry, I don't hear you. Okay, so let's look into details and see what we are looking at. And this is the interesting aspect of spectroscopy. Spectroscopy is not only imaging, it's bringing you a lot of information. So this image here, again, this is a Nano Optics image. Notice that this is the scale bar of 200 nanometers, and you clearly see like these AA topological points and this strange solitons and the AB stacked regions, okay? If you give a zoom here, you also see it, and you can see this information on different aspects. For example, this information here is plotting the intensity of this peak, while this information here is plotting the line width, the width at half maximum of this peak. Okay, and from every aspect, you can remove a lot of information. So, for example, let's talk again about this peak here that I told you. It's a peak related to a second order hexagon breathing, and it has been shown in 2006. This is one of the most highly cited papers that we have in literature. It's, I don't know, tens of thousands of citations. And the reason why this paper is very important is because these fellows, they showed that the shape of this Raman peak tells you how many layers you have on the system. And this is very important for all the developments of, let's say, graphene devices, okay? Because you may want one layer, two layers, or rotated layers, etc. And they demonstrate that when you have bilayer graphene, but here with the regular AB stacking, the shape of this band is like this, okay? So when we do nano optics, we do see shapes that are very much like this one that we have in AB stacked bilayer, and we have shapes that are a little bit backwards, but looks more like a single layer and or uncoupled bilayer graphene. And if you now image where you see such a shape and where you see such a shape, you see that this is exactly at the triangular areas where the graphene rotated back to the equilibrium situation of AB stacking. So this, I would say, is an experimental evidence for what we expected to happen. And if you look now at the regions where we have this strain between the domain walls is where you have this strange shape that is related more to uncoupled layers. Okay. Let's go deeper. This is the phonon dispersion of graphene. Okay, so here again, this very point here would be the only Raman active phonon. So you would have the carbon-carbon stretching that you observe in the usual Raman spectrum. But when you rotate graphene, you enlarge the unit cell in the real space. You reduce the unit cell in the reciprocal space, and this causes what we say it's zone folding. So you take a lot of phonons from the interior of the Brillouin zone and you fold them at the edge of the Brillouin zone, and a lot of modes are supposed to become Raman active. We saw a little bit of this when I showed the imaging of this phonon dispersion relation by rotating graphene. But here the angle is very small, so this generates a high density of states here. And with atomic calculations, what I call atomic calculation is when you do calculations to model electron and phonons in these systems, you cannot rely on the periodicity of the unit cell. You have to really account for every atom movement and on like thousands or millions of atoms. And when you do this, you see that you can look at the structure or vibration of our electronic structure locally. And what these fellows show theoretically is that if you look at the phonons in the high frequency here, they are localized at the strange solitons, at the domain walls. And if you look at the phonons in the low frequency, they are localized at the AA sites. And when we now go with the nano optics and measure it locally, you see that when you come to the AA sites, you see besides the usual peak here that is related to the carbon-carbon stretching, you see an extra peak appearing here that is very much like predicted for those small frequency here. And when you look in the soliton strain region, the domain walls, you'll see a new peak appearing here, very much like predicted theoretically. And you can also look into the width of this peak, and plotting the width of this peak in space, you see that the width also shows the structure. Okay, so to understand this, we have to go deep on the electron-phonon interaction. So let's look this picture that was introduced by Pisana. It's a group in Italy. Okay, this you notice this is 2007. So what these fellows explained was the following. Here it will be the direct cone structure of the electronic structure of graphene. And in this case, graphene is a little bit doped, so you have electrons up to here, okay? Where is green is where you have electrons, and then the electrons are filled up to here, and above are are empty spaces. So usually when the atoms move, as we said in the carbon-carbon stretching, we always use the so-called adiabatic approximation. We just consider that electrons are too fast and phonons atoms are too heavy, they're too low, okay? So we treat electrons and phonons separately, and we extract all the information without considering electron-phonon interaction. However, these fellows, they introduced this very nice cartoon. They said, what happens is very much like if you are shaking a glass of wine, okay? So because the electrons respond very fastly to the phonons in the graphene structure, when the atoms move, the electrons, they are not static, they are not stable. And these generate a very strong electron-phonon coupling. And you cannot treat electrons separate from phonons. So this has been studied by many groups, both theoretical and experimental. And there is a paper from Hishiro Saito in Japan that has a very nice picture to explain this effect. So inside the material, the phonon would be traveling, and then the phonon decays into an electron hole pair. And the electron hole pair decays back and emits the phonon. So the fact that this effect may happen in the material, this has two effects. It changes the phonon frequency because it dresses the phonons with electrons, so they become a little bit more heavy. And this also changes the lifetime of the phonon. And by changing the lifetime of the phonon, you increase the line width of the Raman band. Okay, so this is what is behind the Raman line width. And this has been proved very nicely by an experiment where you measure exactly the line width of the carbon-carbon stretching by gate doping the material. So when the material is not doped, it's at 0, means this level here of electrons is at this point. Okay, so when it's at this point, this is full of electrons and this is empty, so you can generate the electron hole pair. But if you move the doping either to negative or to positive side, what you do is you take the level of electrons and you move above the phonon energy. And when you fill of electrons up to here, because of the Pauli exclusion principle, you cannot decay, the phonon cannot decay into an electron hole pair anymore because it's full up to here. And this also happens if you empty down here, because there will be no electrons to do this electron hole interaction. So what happens is that if you dope the material positive or negative, the line width will decrease because you kill the possibility of the phonon decaying into an electron hole pair, and you increase the lifetime and you decrease the line width. Okay, when this was shown in, as I said, in 2000 something, this it shed light into a lot of phenomena that we already knew in carbon materials, but we didn't fully understand. For example, this is very old graphite ion intercalation compounds. So graphite ion intercalation compounds is the basics of our ion lithium batteries. Okay, so you have a cathode of graphite and you fill of atoms. And of course, these atoms, they dope the graphene. And what they see is that the sharp peak of graphene becomes very broad and asymmetric. And now we understand this is related to the electron phonon interaction. And the same was shown. This is a paper from Marcos Pimenta in '98 when he was in a sabbatical at the MIT. And they showed that when you probe metallic carbon nanotubes, this peak here is very broad as compared to semiconducting carbon nanotubes. So carbon nanotubes, the way you made the tube can be metallic or semiconductor, and you can see this in the electronic structure. Okay, so what we have to do now is let's look with our nano optics, walking with the nanometer precision into this twisted bilayer reconstructed graphene. And what we see is that the G band line width oscillates a lot. Okay, when you move from 1 to 2 and 2 to 3. And you notice that you have the very low levels here. That is when you pass through the AB stacked regions. You have another level when you are on top of when you cross the domain wall, and the same level when you walk through the domain wall, and you have a high level when you are at AA sites. And again, this can be explained by electronic density of states calculations, again atomistic, so that you can look locally. And notice that that peak that you saw that happened in the magic angle, this peak happens at the AA site. And this causes a lot of electron phonon interaction via these let's say, death of phonon generating an electron hole pair. So this explains the picture. And also on the string solitons, you have smaller peaks. The very specific aspect is that the energy of these peaks are by chance exactly the energy of the phonon. All right, and finally, going back to the magic angle problem here, what we are imaging here is the width of this peak by changing the twist angle, by changing the twist angle from 0 to 3. Okay, so at the very small angles, and we see that the width is maxima at the magic angle. So why is it? Of course, it must have to do with something like this, but now you are tuning the width, not with gating, you are tuning the width with the rotation. And I will skip this, the theoretical aspect, okay, that is, again, atomistic calculations, and you build a device, you, on the magic angle or not at the magic angle, you measure the G-band, and you plot what happens with the G-band with gate, okay? So if you do it on the AB stacking, you see exactly the same shape that has been seen a lot. If you do it on large angle, you see something quite similar. But if you do it at magic angle, the dope behavior is very, first, the width is much larger, and second, it doesn't decay fast as this one decays. And you can understand this when you look into the electronic structure. So this effect might happen here. This effect also happens there on the large angle. So again, we have this here that generates these absorption peaks, but at the very small range in the transport situation, what you have here is very similar to what you have there, but not at the magic angle. At the magic angle, you have the flat bands, and you have a very heavy folding that generates a special structure. So summarizing, we have this strong electron phonon coupling in graphene. We see that this is special in the magic angle, and we see that all these effects, they actually are specially localized. And I will skip those just to say that the next step, a lot about nano optics. The field generated by such an antenna is not really homogeneous, is very structured. And this is what we are working out to understand. And with this, I get to the acknowledgements of many colleagues at UFMG, people from Metro, Bahia, and Pará, and those colleagues from US and Belgium, and they were responsible for the calculations. The other are more experimentalist. And with this, I thank you for your attention.
Thank you, for your very clear and impressive talk. And now you have time to some questions, 15 minutes, about 15 minutes.
15 minutos para perguntas. Você acompanhou?
Thank you, Aldo. Very nice talk. Hi. Right here. Front row.
Okay. I see the voices from Rodrigo, but
Very nice. I have a question about the depletion layer results. So right at the interface, besides the charge movement, you also have strain, perhaps. And strain may also shift the G-band frequency. So my question is how you can separate the two effects, because the strain field can also be extended far away from the interface. And a related question to that is, how wide is the depletion layer that you measured?
okay. So I didn't go into details of that Korean paper, but in that paper, the big achievement was not showing that the strain and doping changes the frequency. This was new. What they showed is that when you plot the G band frequency against the G prime or 2D band frequency, the slope of the dispersion of the points is different if you have a strain or doping. So by looking at, because the frequencies are changing, if you plot one against the other, you can know if what is changing it is strain, doping, or something in between. Okay, and in that case, this was behind the graph that I showed that did that oscillation was one information against the other and not just a frequency. Okay, so this was is this okay? And the second is the entire cycle that we saw was 50 nanometers.
Questions?
Hi, Professor. Thank you very much for your nice talk. I have two quick questions. The first one is related to the atomic rearrangement you have shown in the first part of your lecture. I would like to know what is the typical time scale where the sheet of graphene returns to the original position, and if this has a temperature change on the system as a whole. And the second question is about the shape of the nano antenna you have shown. Is there a particular aspect why is this like a pyramid and not like a cone? Could you comment on that, please?
So on the first one, I don't have a good answer to you, just because I don't know, okay? I can tell you that experimentally, there is no study showing the time response for the rearrangement of the sheet, okay? It might have some theoretical calculation or theoretical simulation on those, but I don't know, okay? So on the second, the reason why we don't have a cone but pyramids is technical. It's not because we want it, okay? But when you do this silicon patterning that I showed you, when you make corrosion in silicon, it follows the atomic structure. So it does it by, okay, technically by nature. It's not our choice. If it was cylindrical, maybe the behavior would be, it would also work. I don't know if better or worse, probably better, but we don't have the means to build it.
Hi, Ado. Thank you for the very informative talk. And in that flat band that appears on the magic angle, the electrons there, they should have a very large effective mass and a very slow mobility.
I agree, okay, but probably if you ask Rodrigo, he will answer this with more property. Yeah, I don't have much to say. On this simple-minded picture, I would agree with you. They should have, okay, but I don't know much about it.
Okay, thank you.
Ado, when you have this bilayer, a graphene bilayer, probably there is a size limit, distance limitations in which you can see any effect. If put then a little bit further, you're not going to see. Do you have an idea about this distance? And if the distance is important, it would be able to do the same thing for disulfide molybdenum that already have two layers. So it's kind of difficult to be stacking the layers.
So let me understand your question. When you say there is a distance, are you talking about, for example, the size of the Moiré pattern? Is this what? Okay. So this size is related to the angle, right? So it goes from infinite to atomic distance. So it's really related to the angle you are rotating. And this is being studied in many bidimensional systems. It's not only graphene. You have transition metal decalcogenides, and most of these systems, they have very nice twistronic, let me use this, twistronic studies all over.
Hi, Ado, nice talk. So I just have a question about symmetries, whether you guys have considered emergent symmetries when you twist the two layers and with respect to how the symmetries change from monolayer graphene when you have the two layers twisted, so the emergent symmetries, if you have looked at that, and if so, how that would change the electronic properties and the band structure of the bilayer crystal.
Okay, so let's put it in two levels. Okay, when you have a single layer is hexagonal. Okay, it's and the fact that you have two identical atoms in the unit cell makes that you have the zero gap semiconductor. For example, hexagonal boron nitride has exactly the same structure, but because you have boron nitrogen, you break the symmetry and then you open the gap at the K point. When you do bilayer graphene, when you put one layer on top of the other, you change the symmetry because you have these two layers that are moved one with respect to the other. So you break, well, you create an inversion symmetry at the center between the layers. And this makes that you cannot do it in graphene, but in bilayer graphene, you can open a gap with an electric field. Okay, because when you put an electric field, you break the symmetry of the bilayer, and then you can open a gap and you can control this gap with the electric field. And when you go to twisted, the most, let's say, I think the most important aspect is that for some situations you have an incommensurate system. So again, the rotation, the richness of even the periodicity. The simple-minded picture is that the periodicity goes with the angle, but actually it fluctuates a lot because of incommensurability between the layers. I hope this answers your question.
Actually, generates a second question.
Okay.
Because when you have this incommensurability, you might generate fractal structures in your spectrum, like Hofstadter butterfly kind of thing,
yeah,
but without a magnetic field. That
yeah,
could be very interesting.
Yeah, this has not been studied very much. You are right. Every time you have incommensurability, you have this richness, but these effects are usually so mild that it's hard to see anything. And at least on my ignorance, I never saw any experimental study addressing, these like devil staircase or those things with. And we have to remember also that when you make one twisted bilayer graphene, you are not able to twist, because to see these effects, you would have to twist yourself. Maybe magnetic field could generate some interesting phenomena, but I don't know any of those phenomena that showing up into the experimental results, just because they are too mild.
Hi, Ado. Here.
Yep.
Thank you for the presentation. My question is regarding if the antenna has a specific resonance, and if so, could you make it broadband or push it to longer wavelengths such as infrared and terahertz? Thank you very much.
Yeah. So there are two aspects for you to change. So making it broadband, it's a compromise, because the more broadband, the less effective for a given frequency. So the less it will enhance the field locally. So you don't want to be too broad because you lose the specificity of the resonance, okay? But tuning the frequency where it is resonance, then there are two aspects. One is the size of the antenna, is the L parameter that I showed, and the other is the metal that you use. To couple to the EE laser, as I said here, that is red, gold is very nice. But if you want to push it towards like green, you have to move to silver. Okay, and then again, there are lots of technical details. So gold is very stable in air, silver is very unstable, and you have to work with alloys. And this is actually one of the direction of research that we do. Okay, is generating alloys to move the resonance to where we want.
Hi, Ado.
Yeah,
I'm here. thanks for the great talk. And can you please remind me, what is the angle, which angle or angles the properties of superconductors shown? And other question, the real question, the curiosity is, what is the temperature that we see this superconductor properties?
Yeah. So the angle is around 1.1 degree. Okay, that they have it. Although now they know that this is not the only magic angle. Okay, now they say there are other magic angles, but it was found at 1.1 degrees, and the temperature is I don't know exactly the temperature they use, but it's very low temperature. Is liquid helium, liquid helium. Yeah. So I would guess it's 3 Kelvin. Okay, something like this.
Hi, Ado, here.
Yeah.
Here, right here. Thank you for your very clear talk. And my question it's related to the system, what situation where you deposit your graphene layer or monolayer on top of glass, and the other side you have the talk. So you have shown the structure on the secondary this oscillation. I was wondering if there is some special feature or you would expect on transport property along this interface. Have you thought or looked into that?
No, unfortunately, we didn't, on this specific work, we didn't do any device to really put contacts and play with the transport. Okay. But you are right that it would be very nice to image by changing gate or something like this, because this would be, you are right that things should change and it would be nice to see it, but we didn't.
Okay, thank you. This would be like a quasi 1D property along with that line. Thank you very much.
So we still have 2 questions here. I don't know if how many do you have there, but perhaps are the 2 last ones, right?
Yeah.
Okay.
Hey, Ado.
Yeah.
This
now I can see better.
Okay.
Yeah.
I have a very technical question that is related to the experiment of building these twisted bilayer graphene systems. So I remember hearing sometime a few years ago that you just take graphene and then drop other graphene sheet on top and hope for some angle. So could you please comment on what is the state of the art nowadays for getting these specific angles, 1.1 degrees, really precise, right?
You know what, I removed one slide that you may like it. Okay, so this is how we produce it, okay? So you take, you have a stamp that we produce, use the very same methodology that we use for the antenna. But we stop here and we get, this would be like our machine to pick up graphene, okay? So if you come here, you land this thing, you remove a piece of graphene, and then you go on top of the other, you rotate by the angle you want, and then you do all the stuff that you need to place the bilayer. But you are right that every time you do it, on average, you got 1.1 on average. But locally, it's like if you take a sheet of your bed and do like this, it will never be perfect. So I didn't show here also because it was a lot of detail, but you have kind to fish for the good location. And we fish it looking into Raman properties, into scanning probe properties, and a lot of things for you to say, okay, this is a nice location. Here is where I'm doing my experiment. But we are not able to do like a micron size, perfect twisted bilayer of a given angle.
Okay, so let's thank you, Ado, again. And
So let me just tell you that there is a bus outside. I think everybody knows that go to the Instituto de Física now. Okay.